First, a little bit about myself. I'm data scientist in Dell's data science factory. I joined Dell 4 years ago after I graduated my biomedical engineering degrees. My research, as Xenia said, is in breast cancer detection using exhaled breath analysis and data science methodologies. And during this research, I realized that what I love doing the most is handling data, play with it, investigate it, and make some very cool predictions using the data. So therefore, I decided to work in a company that has data science and has a lot of interesting use cases that we can work on with data science. That's why I chose to work for Dell. During the last 4 years, while I'm working for Dell, I had a chance to work with several business units and leading data science engagements with them. For example, I worked with the cyber solutions group, the supply chain unit, the pricing unit, and now I'm working with the office of the CTO. The project that I will share with you today was a project that we done in the team about 2 years ago. And I would like to first share with you more about our team. I saw from the previous session questions that you had a lot of questions regarding the team structure and some offerings that we can have. So I'm very glad that I put this here in this presentation. So I will first do a short introduction for my team, and then I will tell you about this specific project. I can tell you that I was supposed to present this presentation in Prague on March, but it was canceled because of the COVID-19. So I'm very happy to share it with you here today. So as I told you, I will first have a short introduction to my team. And then I would love to tell you about the data science project lifecycle as we see it in my team. And I will do it by example of predicting future crimes. We will explore the crimes data set, then we'll have a feature extraction phase, and then we will train and evaluate a machine learning model, and I will share with you the conclusions that we got from this project. So the mission of my team is to develop and integrate AI solutions in every possible business process or product in order to help decision-making processes for Dell business units, as well for external customers. In order to do so, our team consists of every possible data people, data scientists and engineers, platform architects, software engineers, and each required role to allow the development and implementation of data science solutions and products in every possible field, as you can see here in this slide. So we have three main streamlines that we work in the team. We are working with Dell internal business units mainly in order to provide consulting services and to help these units accelerate data-driven and AI innovation. But we also giving end-to-end solutions with these business units, which include the proof of concept development, as well as full implementation of data products in the business unit systems. And at the end, it depends on the business unit request. Moreover, we are working with professional services, which is an internal business unit inside Dell that helps us collaborating with external customers to give either consulting services or data science full solutions. So we are working both with internal business units inside Dell. This is our main focus, but we also add and we are having engagement with external customers. This slide is just because I wanted to share with you the innovative spirit of the team. We write patents in the AI areas which related with the business cases that we are working on. And we are also providing data science courses in leading universities. And now we are developing an online version of this data science course. And we do so in order to share how we use data science in the industry in Dell and to expose people to our work. We are now working on online data science course to be taken internally inside Dell at first and then externally. And it will be some hands-on workshop where we share actual code that you can play with and see how you actually can develop data science solutions. We also present our work in public international conferences like this one. We love to participate in internal hackathons as well as the external hackathons and challenges. And all of that in order to expand our data science knowledge and capabilities and expose ourselves to real world problems. Always we want to learn more. Okay, so this is the structure and the mission of my team, and now I will share with you the data science project lifecycle as we see it in my team. It's very detailed slide, so I will go over it on a very high level on the important stuff. So this is the way we work. We work by this workflow, and for each data science project, we first partner with the business or the customer to understand their challenges and define their needs. The next important phase is to consolidate all the data and explore existing data sources and how we can leverage the data to help and solve the business problem. Then we develop the data science proof of concept and build an initial AI solution. This will be the phase that I will focus on today while sharing the machine learning crime prediction use case. And in some cases, when it's required by the customer, we are also convert this solution into a product and we integrate it into the business systems and then have quality checks and production support and everything we need to have this solution on the real systems. Okay, so now we can go and start predicting future crimes. I will start with a short disclaimer. So predicting future crimes is a very complex problem and it depends on a lot of external reasons and parameters. And today I will share with you a very initial but successful solution to this problem. And what we will get is a glimpse to how we approach data science projects. I will share with you the successful solution that we have developed for this initial problem. And you will learn about the fascinating crimes in Chicago dataset. I can share with you that we achieved a very good accuracy using only this initial dataset. But as I said, crimes is something that depends on a lot of variables and parameters. So the model, of course, could be improved. So when I say that we would like to predict future crimes, what do we actually want to predict? So we would like to predict the crime count. We would like to predict the crime count for a specific crime type and specific day and specific police district. And we want to do so in order to help the police understand how to allocate their resources. So an example to something like this is, we would like to predict how many thefts will be taking place next Monday, for example, in police district 11. This is an example of the metric that we would like to predict, the crime count. And in order to do so, we use the Crimes in Chicago dataset. The Crimes in Chicago dataset is a fascinating dataset. I really encourage you to take a look on it. It's very detailed dataset, contains a lot of information about each and every crime that occurred in Chicago since 2001. It's publicly published on the Chicago Data Portal in the City of Chicago website, and it's updating every 7 days. So it's very up to date. This data contains no missing value. It's very whole and nice to use. So this is the data set that we chose to use for this use case. After we know a little bit about what we would like to predict, now, as I promised, we will go over all of the data science project lifecycle phases that we went over. The first one is the exploratory data analysis, where we explore the data to see trends and patterns and interesting things that we think would help us predict future crimes. This is the phase that we spend most of the time on when we are developing a data science solution. So this is the phase that I will share with you the most about it in this presentation. The next phase is the feature extraction phase, where after all of the knowledge that we gained in the exploratory data analysis phase, we are thinking about which features we can extract from the data that we think would help us predict future crimes. After we have these features for each and every crime, then we can train a machine learning model on this data and evaluate it to see how well we did in predicting future crimes. So we will start with the exploratory data analysis phase. This is how the Crimes in Chicago dataset looks like. I put here the most relevant columns from the data. The data contains more than 6 million rows. Each row is a reported crime, which is described by 22 columns. And we have crimes from 2001 until today. And let's go over some of the columns. For example, each crime has its own ID. We have the date and the time when the crime occurred. We have the primary type of the crime. For example, here, it could be narcotics, homicide, theft. We have a short textual description of the crime and a short location description of the crime. We also have information about whether an arrest was made for this crime. And we have location information about the crime, the police district, and the exact location of the crime. So looking on the data this way, it's very nice, but it doesn't really tell us anything. We need to visualize it to get to know it better. And for that, we used an Elasticsearch and Kibana actually dashboard. And here you can see several graphs that we created using this dashboard. For example, we can see the crime count over the years. We can see a nice pattern here from year to year. We can also see the primary crime type. So for example, here you can see that the theft is the most common crime in Chicago. We can also see the crime count across the hour of the day. You can see that most of the crimes occur during the daylight and not during the night. And we can also put all of this information on map and see where is the crime most concentrated in. What's good about this dashboard is that we can dynamically change all of the graphs using clicks on each point of the dashboard that we want to. For example, if I click on theft, then all of the graphs are updating automatically to show me only relevant data that's related with theft. So you can see the difference. And some interesting thing we can see here is that if the crime, for overall crimes, it was concentrated in 2 main areas in Chicago, then theft is more concentrated in this area in Chicago. Now I will share with you more of the graphs that we used for the exploratory data analysis, and I will tell you what we learned from each one of the graphs. So here are 4 types of plottings, and I'll go one by one and share with you the insights that we got from each one of them. So here you can see the crime count across the seasons. It's for overall crimes. You can see that there is a little bit difference. There are slightly more crimes in the summer, but overall it doesn't look like the difference is so high. But if we focus on homicide, then you can see that the count in the summer is doubled than in the winter. So this tells us that in order to predict this crime, we would definitely like to use the season of the year as an input to our model. Another graph is the crime count versus the hour of the day. And again, you see that most of the crimes in Chicago is more during the daylight. But if we focus on specific crime, for example, arson, then you can see that most of the crimes occur during the night and not during the day. So again, the hour of the day is something that I would like to consider when predicting future crimes. Here is another interesting graph where we have the crime count across the months. So you can see 2 interesting trends in this graph. The first one is that we have a decreasing in the crime count from 2010, this graph, dark blue graph, from 2000 to 2015, you can see that there was a general decreasing of the crime count over all months. And we can also see another interesting thing is that in February, it doesn't matter which year we are, in February we have less crimes. And this is of course because February is shorter months, but it's nice that we can actually see this in the data. So again, when we are looking on the crime count over the months, so there is no much difference except of February when we can see a drop in the crime count. There is no much difference across the year. But if we focus on specific crime again, on gambling now, then you see this very interesting pattern. You can see that every year we have more crimes on July and August, and we have less crimes on January and February. So again, and it's also going with the season, but it's more granular information, and the months is definitely, again, a metric that we would like to consider. Lastly, the crime count versus the day of the week. Again, we can see a clear pattern when looking on overall crimes, but focusing on prostitution, we can see that we have more crimes during the middle of the week and not on Sunday and Monday. So the day of the week is again a feature that I would like to consider when I'm predicting future crimes. Maybe someone have any questions, or Ksenia, you would like me to take questions in the end? Whatever fits more.
I think it depends on that how you would like to do that. I think maybe all the questions in the end, or how it is better, tell us.
Okay, so just write questions if you have on the chat, so you won't forget them, and I will take them in the end. Sure.
Okay. Okay. Is it fine?
Thank you. Yes, yes,
Yeah.
sure.
Okay.
Okay, so now after the exploratory data analysis phase, we can go to the next phase, which is the feature extraction phase. And based all of the knowledge that we gained in the exploratory data analysis, then now we can extract feature from the data that we think would help us predict future crimes. So based on all the analysis that we made, maybe you can try to think which parameters I would like to consider when predicting future crimes. Try to think for a second. So here are the features that we initially used. So we used the season, the month, the day of the week, as I shared with you in the previous slides. But we also thought that there are more features that might be related with future crimes. So we also put the day of the month. We insert the weather, the temperature in specific days. This is an external data source. It wasn't appeared in the data set, but we chose to get it from external data source because we thought it would be significant. Because we know there is a connection between the season and the crime type. So maybe the exact temperature would help us predict future crimes as well. I would mention here that we have the temperature for historical days, but for the future, we don't necessarily have the temperature. So for future days, we are using the temperature prediction, of course. Another data source that we used, external data source, is the holidays. We saw that there is a difference between the weekend and the middle of the week. So maybe when it's holiday, something would be different with the crimes. So we also insert this information to our modeling. And we insert a binary feature that indicates whether it's a weekend or not. After having all of these features for each one of the crimes, we would like to predict our metric, and we'll go to the training of the machine learning model phase. I will share with you the model, the machine learning model that we used, and I will share with you afterwards in which ways we evaluated this model. So we chose as the first step to use the most simple machine learning model that we can. We chose the linear regression model, and we chose it first of all because it's very simple. But another reason is that we can explain the results after using this model. We can see which parameters affected the output, and this is why we chose this model, because it's very easy to explain to the customer, for example. So in the linear regression model is a model that model the relationship between a dependent variable, which in our case is the crime count for a specific day and specific crime and specific location in Chicago. And it modeled the relationship between this variable to one or more explanatory variables. In our case, it's all the extracted features that we took from the data in the previous phase. So this is the machine learning model that we used for training. The next phase, before I will share with you the results, is the evaluation phase. And here I would like to show you which metrics we used to evaluate the model. So these are not the results yet. It's just me showing you how we evaluated the model. So we did this with this graph, which shows us the predicted value from the model versus the actual values that comes up from the data. And each point in this graph is the crime count for a specific crime type, a specific day, and specific police district within Chicago. So for example, this point would tell us that the actual number of crimes in this day was about 27, but our model predicted it to be 4 crimes in this day. So for this point, our model didn't do so good. And in this graph, we would like to see the points well spread across the y equals to x line, because that would tell us that our model perfectly fit the data. Another metric here is the Pearson correlation, which tells us the correlation between the predicted value and the actual values. And again, I would like this number to be as close as to 1 as possible, because this would tell me that the predicted value are equal to the actual values when this Pearson correlation is 1. So I would like it to be as high as possible. Another metric that we use to evaluate the model is R-squared, which is the common metric to use when you are running a linear regression model. You have here the formula that computes this number, and this number will go from 0 to 1 and would tell us how well the model approximates the real data points. When it will be equal to 1, it will tell us that the predictions are perfectly fit the data. It's the ideal state. R squared equal to 0 would tell us that the modeled values cannot be obtained by the model, means we cannot predict the metric that we want to predict, and any number between 0 to 1 would tell us the percentage of the variability that can be explained by our model. So again, we would like this metric to be as close to 1 as possible. So these are the two evaluation measures that we used, this graph and this R squared. And now I will share with you the preliminary results from the modeling. These are the preliminary results from the modeling. As you can see, it's not so good results. You can see that the points are not well spread across y equals to x line. You can see that even though the actual values from the data could have crime count between 0 to 30, our model weren't able to predict a number that is higher than 10 for some reason. And the R squared again over the training and the testing set is 0.56. It's very low. So these were the preliminary results. And in this phase, we were really frustrated. We thought that we have done a very extensive exploratory data analysis on the data. And we didn't know what exactly went wrong because we really believed in this data. And we tried to think what we can do in order to improve the modeling results. So at this point, we decided to take a step back and to the feature extraction phase and think what information we have in the data that we haven't used until now. Try to think about it for a second. What features we can extract from the data that we haven't used until now. So at this point, we chose to look at the data from different angles. For example, here you see a graph that shows the theft count as time series. You see the theft count for each day. And it's like a time series. And when you look on the graph and on the data in this way, and you think, I would like to predict how many crimes will be taking place on Monday. So maybe I can use the crime count from Sunday in order to model this. Maybe I can use how many crimes took place the Monday before in order to predict the next Monday. Or maybe it should be Thursday. We don't know exactly which point in time we would like to choose in order to predict future crimes, but this is definitely an information that we haven't considered yet in the model. In order to figure out what is the best time frame to use, we use the autocorrelation function. The autocorrelation function is a very nice function. It's a little bit hard to digest when you see it for the first time, but I'll do my best to explain. So the autocorrelation functions tells us how well we can predict the future based on past values as function of the time lag between these 2 points in time. So actually, the autocorrelation function takes as an input all the data that we have, and the output from the autocorrelation function is this graph that you see here that contains a very nice pattern. What we can learn from this graph is that in order to predict how many crimes will take place on Monday, for example, then we should consider how many crimes took place the Monday before, because we see this peak on 7 days, on lag of 7 days. We can see the same peak, of course, for 14 days and 21 and 28 days. So what the autocorrelation function tells us basically is that we need to use a 7 days lag. If you would like to predict how many crimes will be taking place on next Monday, we should insert to the model as an input also how many crimes took place the Monday before. Another interesting point that I would like to mention about this graph is I highlighted the main peaks here, but you can also see a very high peak here on one day. What it means that in order to predict how many crimes will take place on Monday, for example, you should consider how many crimes took place on Sunday. But we didn't want to use this kind of information for the model because we would like to be able to inform the police enough time ahead before the actual crimes. And if we will wait until we have all the data from Sunday, it won't be good enough to predict how many crimes will be taken on Monday. It would be too late. It will be tomorrow, and we didn't want to take this approach. So we only used the historical data starting from 7 days backwards. So actually, these are the features that we have inserted into the model in the preliminary phase. And now we can insert new features, the crime counts of 7 days before the day would like to predict, as well as 14, etc. Because we saw from the autocorrelation function that it should be significant for the prediction. We also inserted the crime counts from 1 year before because we applied the autocorrelation function to monthly data as well, and we saw that there is connection from 1 year before as well. I haven't shared the analysis here, but we figured it out as well. After having all of these new features, now we can train a new machine learning model and evaluate it again to see how well we are doing using the new features. So these are the results using the time-related features. You can see that these are very good results. The points are well spread across y equals to x line. You can see that the Pearson correlation between the predicted and the actual values is is very good, and the R-squared values are very good as well. And just for comparison, these were the preliminary results that we had from the model. So you can see the improvement just from using these simple features that related with the time. These features weren't available as raw features in the data. We had to think about them and engineer them. But after using these features, we get a very good results from the modeling. And these R-squared values are higher as well. So these are the results. I haven't mentioned it until now, but these are the results for all of the crimes in Chicago. And after having these results, we can go and investigate more the results to see other interesting patterns in the predictions. So the first thing that we did is to put the evaluation metrics for specific crime types. So here you can see the results for theft. You can see that the results are still looking good. The points are well spread across y equals to x line, and we still have good R-squared values. But for different crimes, the training and the testing R-squared is very low, and you can see from this graph there is nothing, no significant pattern here between the predicted and the actual values. And here we can start and think about reasons why it's working for specific crimes while it's not working for other crimes. And the main reason we thought to be a problem here is that in most of the days, there are no prostitution crimes. You can see it here. Most of the points are, the actual value is 0. And because of that, our model didn't have a lot of data to be trained on, and therefore we couldn't predict it for this specific crime. This is what we think. Of course, there could be a lot of other reasons. As I told you, crimes prediction, it's a very complex problem. There could be a lot of external sources of information and other features that we didn't include in the model. But this is our assumptions using this data set. Another thing is regarding the training and test splitting. Up until now, we used 2014 to 2015 for the training set, and we tested the data over 2016. And this is the data that the results that we got from this data. So you can say maybe if I would train the model over a longer period of time, maybe I would be able to get better results. So the answer here is no. We tried to train the model from 2012 to 2015 and test it on the same year, and we get the exact same R-squared and very similar results here. And we think it's because adding more data to the model is not helpful in order to improving it. This data could be no longer relevant to the model. It's crimes, it's something that could be changed over time, and adding more historical data didn't improve the model. Okay, so I shared with you all of the work that we did on the crimes in Chicago dataset for predicting future crimes. We went over the exploration phase and then the feature extraction phase, and then we trained and evaluated the machine learning model. And now I would like to share with you some of the conclusions that we had. So first of all, when modeling goes wrong, you should step back to different phases of the project life cycle in order to try and improve the model. As you saw here, we got back into the feature engineering phase and try to think about more features that we haven't considered. But you can go to any other phase of the data science project lifecycle to try and improve your results. For example, there could be a problem in the data preparation phase. That could be a problem of the understanding of the data. And then you should go to talk to the subject matter expert that knows more about the data. Maybe the approach is wrong. So when something is going wrong with the modeling, then you should go to previous phases in order to try and improve it. Another thing is about the training data. Should we use as much data as we can? So we saw that the answer is no. In our case, the modeling results didn't improve when we add more historical data, but the results could be even worse. And sometimes adding more historical data to the model sometimes could decrease the modeling evaluation metrics and make the model work worse, because when we are dealing with time-related data, some historical data could be no longer relevant and it could just confuse our model. Another conclusion is regarding the time window. And here I would tell you that it depends on the amount of crimes. As you saw, for prostitution, our model didn't work well. And what I'm referring here with the time window is that we choose a one-day time window. We wanted to predict how many crimes will be taking place on Monday. Because of that, we have a lot of observations of zeros in the data for prostitution, and therefore the model weren't able to predict this crime. But maybe if we will consider to enlarge the time window, maybe if we look on a weekly time window and check how many prostitution is occurring over a week, maybe it will lead to a point where we have more values in the data, and then we would be able to predict it. How many crimes will be taking place next week? The model would be less specific, but maybe it would be better. And the last thing is the autocorrelation function that helped us to find significant lags. So this is definitely a conclusion we are taking with us. When we have time-related data, we should use the autocorrelation function to reveal interesting trends and interesting time-related issues in the data. That's it. Now I can take questions.
Yeah, there are already quite a lot of questions in the chat. And the first was, which tools do you use to visualize the data?
Yes, so we used Elasticsearch to hold all the data, and we use Kibana. Maybe I can write it down in the chat. So Kibana is the platform that we used in order to visualize it. And Kibana uses data that sits on Elasticsearch. Using these two platforms, we were able to create these dynamic dashboards.
Okay, great. What is the standard of the features that could be selected into the data set?
What is the standard of one feature? Could be. I'm not sure I'm getting.
Could be.
Not sure I'm getting the question.
Let's find the author and unmute him just a second. Just a second. Just a second.
Hello.
Yeah.
Hi. Thank you for presenting such a wonderful slides. My question is that I see that you have a lot of variables used into the data set of to predict the crimes. But how do we know one of the feature could be helpful for the prediction, or the other feature maybe not such valuable to the prediction? Is that any standard, or we have to depends on the prediction results and go back to see if this feature is usable or not.
Okay,
Thank you.
now I get your question. Thank you. So maybe I will have two approaches here. One of them can be used before modeling and one of them after modeling. The first one is before modeling, you can run a correlation analysis to check the correlation between your variable and the output variable. In our case, it was the crime count. Check the correlation and then take only features that are highly correlated with the output metric or the predicted metric and insert them into the model. In this case, I wouldn't recommend it in all cases because sometimes you can miss some features that are unique for specific observations, and then you will miss these features in the analysis. Another way that I can think about here is after you are performing the training and see your results from the evaluation, there are some techniques such as SHAP values and line package that you can use that can tell you for each observation which features led to the model decision. Why they can help you understand which features was the most important for your prediction. And then you can use these results in order to choose specific features and try to perform the model again. Another thing I can suggest here is do a lot of testing, remove and add features to see which combination of features give you the best modeling results. I guess that would be my answer, but I gave here just 3 approaches. There are more approaches. Yeah.
Yeah, thank you very much. Yeah.
Mm-hmm. The next question, what happens if we miss some feature that could help to predict the future crimes more accurately? Is there a way to know which features can contribute highly without actually creating the model? Also, how to choose a prediction model for the problem just by looking at the data?
Mm-hmm. Okay, so there are several questions here. So in this case, I gave my disclaimer at the first place. I guess that even in this case, we miss a lot of features that could help us predict future crimes. I would not go into it, but you can assume that there are a lot of external features that we didn't use that could affect when and where next crimes will occur. It could be a lot of reasons. What happens in the world today, the COVID-19 could affect it, and we weren't able to insert it into the model before we knew about it. There are a lot of features that I guess could help predict future crimes more accurately that we didn't use. Regarding the second questions, I guess before creating the model, it's just the previous question that I answered. You can run some correlations analysis and more visualizations like we did to try and understand which features could affect future crimes. And this is why I told you that the exploratory data analysis is a critical phase, because in this phase, you can learn which features could contribute to a more accurate model, and how to choose a prediction model for the problem just by looking at the data. So first of all, our approach in the team is to start with the most simple prediction model and then take it from there. If you see that your results are not so good, then you can try more complex model. We choose the most simple models because they are very easy to explain. We are working with our customers, with our subject matter experts that are not necessarily knows a lot about data science, and we should, after we build a model, we should convince them why the model works. So this is why we choose the simplest model at first. And if it doesn't work, we will take it to a complex model. You see here, we use just a linear model. Maybe the next step here could be using nonlinear model. And of course, it depends on the data, on the metric that you would like to predict.
The next question on the model, are we equating social engineering in order to predict the crime count?
Yes, so this is some external resource that we couldn't use because we didn't have this kind of data. So no, this model we've developed are not using any social information in order to predict future crimes.
Then there is not a question, but more a comment that there are specific crime-related features. As I got it, it is the question from Diana. Diana, can you maybe comment what you meant and what is it about? Let me check if Diana is here. I think yes. No, yes. Diana?
It wasn't actually a question. It was just, I was answering.
Comment.
Yeah, comment.
Oh, okay, thank you.
Okay, I got it. The next question is then, linear regression could show dependencies, but it's a weak predictor.
I definitely agree. We chose the most simple predictor at first. We could apply more complex ones, but because we had pretty beautiful results here, then we chose to keep it. But yes, definitely, if we'll try to perform another model here, then maybe the results would be even better.
Then again, I think it's more a comment. Don't you think it's a perfect problem for deep learning models? Maybe, yeah. Can you share your opinion?
So I'm not sure about it. First of all, because we saw that even using the most simple machine learning model, we got pretty good results that we also can explain. I will choose deep learning models when there are some dependencies between the variables that I can't know of, that I can't see in the first exploratory data analysis. That's where I will choose deep learning models. But again, maybe applying this model to the data would yield better results. Definitely could be.
I can imagine that such a model can predict thefts, but how to deal with homicides? Can it be predictable?
Great question. That's why I haven't showed you what were the results for homicides, and I showed you for theft. It would be the same answer for the prostitution concern that I shared with you. We don't have, gladly, we don't have a lot of data in these cases. Thefts happening much more from homicides and prostitution. So our model weren't able to predict well for this kind of crimes, and it makes sense, right? There are much more indicators, much more parameters we should consider in order to predict such crimes. Some social information, as someone mentioned before, and a lot of external parameters that should be considered, and even then I think it would be extremely difficult to predict this kind of crimes. So it makes sense.
Okay. The next question is, how many crime types are there in the data set? Do you train separate machine learning model for each type of the crime?
Okay, thanks. So there was about 30 crimes in the data set. the most common crimes are the most predictable crimes, as you can imagine. And regarding training different machine learning model for each crime type, so this is definitely should be one of the next steps of this project. Definitely, maybe applying separate machine learning models would yield better results for some of the crimes.
Thanks. How do you normalize each feature as numeric?
How do you normalize each feature?
Each feature as numeric.
So do you are you considering the categorical feature?
Yeah.
Yeah. So I have a question about the question. So
yes, Vincent, if you are here, can you please unmute yourself and tell us a little bit about your question?
Yes, I mean, for each feature, it is used a different normalization method, or not.
Normalization. Okay, so I think now I get you. To get the numbers between 0 to 1. So in this case, I think we tried both, like not normalizing the numbers, but then the weights of the linear regression would be different for each one of the features. So the second way was to normalize them between 0 to 1, and then the weight of the parameters for the linear regression would indicate what was the best features to use for predicting the crimes.
Mm-hmm.
Okay, thank you.
Choosing model is very simple. Just load the appropriate Python model. Moreover, the interface is very similar. What about using several models in parallel?
Mm-hmm. Yes, I definitely agree with you. Trying and other models is very easy to use in Python. Even though we didn't do it because we got good results from this modeling. And we also ran this project as part of an exercise. We didn't really provide this model to the police of Chicago, for example. So we haven't tried to fine tune and try to find the best model that would change the accuracy a little bit more. But I agree, it's very easy to do. And I would choose your approaches when I would like to improve the results even more. Mm-hmm.